KPI for exoplanet atmosphere.
All right, thank you so much. And I'm really excited to be talking now because everybody has already talked a lot of introduction about high resolution exoplanet atmosphere, so I can skip through some stuff. No, I'll just go slowly. But I'm talking on behalf of a team that has been working with a lot of the KPF or atmosphere data. So the team is listed here, and I wanted to especially shout out their grad student, Aaron Householder. And he's been doing a lot of this work, and he's going to be leading the first paper and most of the results I'm showing from that. And also here, this image I'm showing is a really cool kind of stylized cross-correlation detection of iron in the atmosphere of WAS 76, and this will become important. But this is real data that's been a bit manipulated to make it look cool that Alex Polanski put together. Okay, so most of the time when we think about characterizing exoplanets, we think about characterizing exoplanets with transit transmission spectroscopy that's performed at low resolution. And so the idea for that is that you have a time series observation where you look at the transit of a planet in front of its host star, and you do this at multiple wavelengths. Oh, I got stuck. Okay. And you do this at multiple wavelengths, and at wavelengths where there's some opacity source that is absorbing in the planet's atmosphere, the planet will look larger. So here's a really beautiful example of the first transmission spectrum from JWST that was published of WASP 39. And so it's plotting transit depth. So an increase in transit depth is kind of opposite of what you would think. So an increase is actually where you see a molecule. So there's a huge increase in transit depth around 4.2 microns, and that also corresponds with carbon dioxide, where that has opacity. And so this is a really strong detection of carbon dioxide in a planet's atmosphere. But you can actually also do this at high resolution. And so we've talked about this before, Luke's talk yesterday. And you can both do this for single lines and for forests of lines where you do this with cross correlation. So this is just a little animation of how you would do this with high resolution by taking advantage of the fact that we get really good velocity resolution, and we can actually resolve the motion of the planet and use that to distinguish it from the host star. So this is an example of what you would see if you were looking at the sodium doublet. So the host star has constant sodium absorption in time, and the planet only has this excess absorption that happens during transit. And when the planet starts transiting, it's moving towards us, and so it's blue shifted, and at the end of the transit, it's moving away from us and red shifted. So we can remove kind of that constant in time absorption from the host star and be left with the planet. And other people have talked about this before, but high resolution is really powerful. And while JWST is doing a lot of really excellent science for exoplanet atmospheres, it can't do everything. And high resolution has this really great protoparameter space that you can't do with instruments like JWST. So this is an example showing how important high spectral resolution is for the detection of iron in particular here, but also all refractory species. So these have narrow lines that are pretty far spaced apart from each other. So when you go to low spectral resolution, I'm showing in black here, basically you have a flat line at a resolution of 1,000, but at a resolution of 100,000, you have these really beautiful large peaks. For molecules that have more dense forest of line, even at a resolution of 1,000, you can see pretty clear different bandheads of water. And recently, there's been a bunch of work from the theoretical side, how refractory species can be a really nice lever for understanding planet formation and really complements carbon to oxygen ratios, because refractory species trace rock formation and different ice lines in a protoplanetary disk that carbon to oxygen ratio by itself struggles with some degeneracies. Okay, so you can also do this with cross correlation if you don't have these really strong single lines like a sodium doublet. you have a forest of lines, you want to combine all of those lines together with cross correlation. And in practice, you have a raw time series spectrum. You can clean that up to make all of the lines consistent in time. Then you can remove that average stellar line profile, and also any tellurics are usually pretty stationary in time. You're kind of left with noise. You cross correlate that with whatever atom or ion that you want to find. And you're left with a cross correlation map where you get excess absorption along the velocity of the planet. So here we're showing a detection of chromium in the atmosphere of WAS 76. And so in the last talk, Stephen talked to us about obliquities. You can see that this white here, that's actually the obliquity signature that Stephen was interested in. So one person's trash is another person's treasure, and obliquities are our trash. So for the rest of the talk, we just mask those out. We don't care about them. Okay, so that's kind of what you do, how to get these signals. And so what we're doing in practice, the goal that we have been trying to do with KPF as a first step is to have an additional public pipeline that takes what you get from the KPF DRP and turns it into a nice flat spectrum that is easy to do atmospheres with. And we will be making this public once we have a good working version. So we'll do blaze correction, combine the orders, combine the science fibers, and we hope to have something that's really easy to put into. We're not going to do telluric correction, but something that's easy to put into code that does telluric correction. And so this is just a really quick example of, we've done some testing on different methods to do all of these different things. And in a paper, we're going to kind of lay out what we find as best practices. So we found good results doing fits to flats, and that really nicely removes both the blaze function and fringing that is in the red arm of the spectrograph. And this down here is just a shout out to the DRP. On the edges of the orders, there was some issues with the wavelength solution, but in the most recent download, I didn't see any of these issues. So you can see here, the absorption lines do not line up in the 3 science fibers. In the most recent download that was just downloaded a week ago, I don't see any of these issues anymore. So thank you so much for DRP people. Okay, so as a test case, we wanted to study a planet that has been really well studied in a lot of different other instruments. So this is WAS 76. It has been studied at high resolution with Maroon X, with Espresso, with HARPS. So it's a really good test case. So you can see iron has been detected in all 3 of these. This is just different ways of showing a detection. I think Luke showed these before, but basically in 3 transits, you're getting a signal to noise ratio of 13 for Maroon X. In 2 transits, a signal to noise ratio of 20 for Espresso, and in 4 transits, a signal to noise ratio of 10 in HARPS. And in 1 KPF transit, we get a signal to noise ratio of about 14.5, which is on par with Espresso. So that's really, really good. We also detect a bunch of other refractory species. They have already been detected, but it's really nice to see that we are detecting lots of things. So not only do we want detections, but we also want to make sure that the values that we are getting are consistent with what has been gotten before. And so this is showing the sodium doublet in the exoplanet's atmosphere using kind of the method that I had a cartoon of before. And this is really high signal to noise ratio of a sodium doublet in a planet atmosphere. So that's really exciting. And comparing the line depths that we get for both the doublet lines, KPF is in purple, so it's basically right in the middle of all the other detections, and it has a pretty low uncertainty, and they're all consistent with each other. So that's great. WAS 76 also has this very famous asymmetric iron absorption signature that was first seen in Espresso by David Ehrenreich in 2020. And so you can see at the end of the transit, we have a blue shifting of the planetary absorption lines, and at the beginning of the transit, not as much blue shifting. And this is due to potentially iron condensation across the surface of the planet. But we also resolve this same asymmetric signal of less blue shifting at the beginning and more blue shifting at the end. Okay, so that's just our first look, and it's showing that we are doing really, really well with atmospheres with KPF. So the goal is to do a survey of exoplanet atmospheres and to answer some key questions. And what's really nice is that anytime somebody goes out for an obliquity measurement, you can do atmospheres for free if the planet is has the right conditions. So I'm showing here everything that has time series transmission observations or time series emission observations. And you can see that we have a pretty large sample that has already been taken or is planned for the future. And some fun science that we can do with this sample. So the planet that I showed you before, WA76, it's one of these ultra hot Jupiters where it has metals in the gas phase. And we're seeing that in a bunch of planets. The hot Jupiters, we don't see any metals. They only have sodium and potassium. And the traditional explanation for that is that as a planet's pressure temperature profile crosses condensation curves for different cloud species and condensates, that species is removed from the planet's atmosphere. And so you can potentially trace cloud formation. However, what we're seeing is not exactly that. We're seeing that some planets that have hotter equilibrium temperatures seem to have no metals, and some planets that have slightly cooler equilibrium temperatures have more of these metals. And also, it doesn't seem like we're removing these one at a time. It seems like the planets have all the metals or none of the metals. And so this is just super preliminary, but that's some of the questions that we hope to be able to answer with this survey. So I'll just leave up my conclusions now and take questions.